this lecture, we want to discuss some specific circuits that are important to biomedical signals and biomedical signal measurements. So most of you have at least had an undergraduate course in circuit analysis. So most of these circuits should be familiar to you. But as we go through, I'll discuss the use of each one. So there are several key circuits that are used to perform basic signal processing on data that come from transducers, because rarely is the data that comes from a transducer in a useful form. Sometimes the voltage is too low, it's often noisy, it may not be in the right form. So we use amplifier and filter circuits, summers, differential amplifiers, integrators, differentiators, and other circuits in order to get the signal in a useful form. Most of these circuits are active circuits, which means they use an op-amp or a transistor. So in this module, we primarily are focused on circuits that are op-amp based. This is an example of an op-amp equivalent circuit. In general, you have two inputs, the inverting input and the non-inverting input, also known as V1 and V2. When there's a differential voltage between V1 and V2, then a current flows through this differential resistance R sub D. This differential voltage is multiplied by A, the gain of the op-amp, and that generates an output voltage source. So you have A times V2 minus V1. Any current that flows to the output terminal V0 has got to pass through this output resistance R sub 0. So this is basically the equivalent circuit of an op-amp. Let me go back just a moment and talk about an ideal op-amp. In an ideal op-amp, we would assume this internal resistance R sub D to be that basically an infinite input resistance or infinite input impedance is seen. We assume this output impedance R sub 0 is 0, and then we assume this gain A when the op-amp is what we refer to as open loop, meaning we just have connections to the input and connection to the output, but there's no connection that feeds back from output to input. So basically, the gain then would be infinite. So that's an ideal op-amp, and generally, the other thing is that op-amps have to have external power supplied. As a general rule, if the op-amp voltage exceeds the external power supply, then you're no longer in a linear range. So for first order approximations of how op-amps behave, we usually assume we have an ideal or close to ideal op-amp, and we also assume that we're operating in the linear range. If not, then we have to then model these components of the input impedance, the non-infinite gain, and the output impedance. So the first and most simple circuit that's used is the inverting amplifier. The basic inverting amplifier is used to provide gain or amplification of a signal. When incoming signal frequencies are relatively low, then we can use just a simple resistive circuit. So I believe in the next slide, a figure is shown. Not yet. Okay, and also sometimes, in addition to that, we want to add a DC bias. So one of the problems is that a lot of times signals that come in often have a DC offset. And if you have a DC offset or a DC bias in your signal and you put that into an amplifier, if the DC is significantly higher than the time varying part of the signal, then basically what happens is you saturate your op-amp. And so sometimes what you will do is, in addition to the amplifier circuit, you use a summer circuit that provides this balancing or offset signal. Okay, so here is the figure of an inverting amplifier. So this is what was described in 2 slides back. So in an inverting amplifier, you have into the negative input of the op-amp, into the inverting input, you have an input impedance and a feedback impedance, called feedback because it connects back from the output to the input. The non-inverting input is grounded. So what happens is current flows from the input V sub I to the output V sub 0, and the output voltage effectively amplifies the input voltage. So the ratio of the output voltage to the input voltage is negative times the feedback resistor over the input resistor. So if you set this ratio of feedback to input resistor to be 500, then basically what this circuit will do is it will take your input voltage, it will multiply it by 500, and it will make it negative. The reason it's negative is it comes to the inverting input. So basically, as long as the input voltage does not exceed the power supply that's hooked up to the amplifier or to the op amp, and that's usually something that's given in specific op amp specifications. It can range anywhere from 3 or 4 volts to 13 to 15 volts, just depending on the type of op amp and how it's spec'd. Anyway, if your input exceeds that external power supply voltage and the rating on the op amp, then basically you will not get any additional input or output voltage. So this is why it's important if your signal comes in with a DC offset, that DC is also going to get amplified. So it's important to set this up where you don't have that DC offset. So here's an example of that. Here's an example of an input voltage that has this offset here. And you can see that if the DC offset were just a little bit higher, then the input voltage would exceed this 10 volt level, and so you wouldn't actually get to see an amplification of the shape of the signal because part of the signal would exceed saturation. So you don't really duplicate your signal if you have a DC bias or DC offset in your signal that's too large. Example of this, it's not at all uncommon when making an EEG measure that you have some just DC level that's their background in your voltage that can come from a number of sources. A lot of times it even comes from, say, the fact that you have some DC on your ground. So because of this, what you would like to do is you would like to take this little signal VI and you would like to shift it down so that it's centered around the 0 voltage axis, and that way all of this then would be amplified by the input resistor. So what you do is you build a summer circuit. So the summer circuit is the part to the left of where the feedback resistor joins in, and basically it's combining two things. It's combining a summer and a voltage divider. So what happens here is you have a 20K and a 5K resistor. The 20K is set up so that you get a ratio of whatever your V sub B is over 20K plus whatever your V sub I is over 10K, so that you're effectively adding that bias voltage in. And you can move this to the negative side. This is a voltage divider, and so how much bias voltage you apply depends on how much you need. So if you move this slider to the negative side, then it's basically applying a negative voltage, so VB becomes negative, which then is what gives you this factor of subtracting VB over 2. So that's why this is chosen to be 20K instead of 10, so that you get this VB over 2 factor. So it's called a balancing voltage or an offset voltage, and basically it just selects the amount of voltage to add to the input signal. So what actually comes in then to your amplifier is just this shifted signal. Now, because the input voltage is applied here to the 10K, but you also are adding this particular voltage, then what you have to do is your new input voltage is considered to be the sum of these two voltages. And so your equation, because op amps are linear operations, you can consider basically each one of these inputs to be like a inverting amplifier. So the V sub I input would have a minus RF over RI. The V sub B input would have a minus RF over RB. And so when you do some algebra and simplify that, you can get your output in terms of your input and your bias voltage, and you can see that we have a gain of 10 here. So, once again, this is done combining basically two circuits, the summer circuit and the inverting amplifier, so that you accomplish this ability to shift your voltage. Now, sometimes we want an amplifier that doesn't invert. Usually that occurs if you are concerned about the phase of the signal, because when you invert, you introduce a 180-degree phase shift. And sometimes, for various reasons, you don't want that. Most of the time, in biomedical signal processing, you are not trying to reconstruct a signal, you're just trying to analyze it and pull data out. So you often don't need the phase, but should you need to preserve the phase, you might want to not have that 180-degree phase shift. Also, sometimes for various reasons, you want to use something called a follower circuit. And the follower circuit is done so that you basically aren't trying to amplify the signal, but you might be, for whatever reason, trying to isolate your input from your output. And so you're taking advantage of the infinite input impedance of the op amp, basically reproducing the voltage that appears at the op amp input. So here's an example of a follower circuit shown here in figure A. The input's actually applied to the non-inverting part of the amplifier, and then you can see the output is just taken at the output. There is a short between the output and the inverting, and so basically what you get there is you get just a follower circuit that reproduces the voltage output equal to the voltage input. In the second figure shown is a non-inverting amplifier, just configured slightly differently. The output over input can be given in this configuration. Notice the input is going to the non-inverting terminal. The inverting terminal is grounded, and so you get a slightly different relationship. The output over input voltage, rather than being negative RF over RI, it's RF plus RI over RI. The only disadvantage of this is you cannot independently necessarily select a feedback to input resistor ratio. So if the input resistance changes for whatever reason, your ratio might be a little more difficult to adjust. So once again, if the feedback resistor is, say, 2 orders of magnitude above the input resistor, then this is less sensitivity. Now, sometimes, in fact, most of the time, biomedical signals contain a lot of noise. And sometimes we can deal with this noise by filtering, but other times the noise is in the same part of the frequency spectrum as the signal. And so it can be a problem to try to filter noise out, because you'll also filter out important signal. So you need a different approach. And one of the most fundamental approaches is, rather than using a straight amplifier on a single transducer, is to use what's referred to as a differential amplifier. And so what you're doing in a differential measurement is you're actually measuring something in 2 locations or using 2 sensors. And your expectation is that both will contain relatively the same level of noise. And the same type of noise. And this is not like random signal noise. This is noise like if you're trying to measure, for example, a signal in a muscle, and your heartbeat signal is appearing because the transducer is picking up the heartbeat. So that would be considered noise because it's something you're not interested in. So what the differential measurement does is it takes signal number 1 and it subtracts signal number 2, and there's an assumption that if the probes are similarly designed and the source of unwanted noise is well defined and characterized, then taking the difference will eliminate the noise. And so what this can do is it doesn't completely eliminate the noise, but it definitely improves the signal to noise ratio. So common mode is a term that refers to noise or extraneous signals that appear across multiple measurement channels. And basically, when we use a differential amplifier, it rejects the signals that are common to 2 channels, and it amplifies the difference in the signal. So here is an example of such a circuit configuration. The right side is basically a 1 op amp differential amplifier. So it's going to give you the difference between the input here at the inverting input and the input voltage at the non-inverting input. But the problem is it has a low input impedance. So what is often done is the circuit on the left side is used initially because it's sort of like a follower circuit with a selected resistance on the output. And so this circuit is used initially to give a high input impedance and gain, and then it's combined with the 1 amp amplifier so that you basically then provide the difference amplification. So use both of these circuits together, and basically the output voltage is given by V4 minus V3 times R4 over R3. So those can be found here. Here's V4, here's V3, here's R3 and R4. This is also R3. So when they're combined, you basically call this an instrumentation amplifier. So the difference between an instrumentation amplifier and a differential amplifier is the instrumentation amplifier includes this left-hand part of the circuit that's there to give you a high input impedance. So you basically accomplish a high input impedance, a high, what we refer to as common mode rejection ratio, and a gain that can be adjusted by adjusting the resistor R1, which is this resistor here in the instrumentation amplifier. This is widely used in measuring biopotentials like EEG, EMG, because it can reject that 60 hertz noise that shows up on such measurements that are done in biomedical engineering labs. So CMRR is the common mode rejection ratio. The gain is V3 minus V4 over V1 minus V2, and that's given in terms of the design resistors in the circuit on the left-hand side. Another commonly used circuit that has kind of a completely different application is the comparator circuit. A lot of times we're using a comparator circuit when we have some kind of a reference and we want to know is our output greater than or less than the reference. That's typically a voltage reference. It works because basically what you're doing is you're using this concept that an op amp will saturate, and it works by intentionally causing the op amp to flip between a positive and negative saturation. So here is what the comparator circuit looks like. Basically when R3, this resistor here, is equal to 0, then the output voltage will indicate whether this input plus a reference is greater than or less than 0 volts. As R3 gets larger, you have a little hysteresis, which means right around the reference, you've got a little bit of memory of the state of the system before. So it's highly desirable, if you don't want that, to have your resistor to ground as close to 0 as possible. But basically what happens is your output voltage will flip from 10 volts to negative 10 volts, or 13 to negative 13, just depending on where this op amp saturates, based on the relationship between the reference and the input voltage. So you're intentionally driving this op amp into saturation. And finally, the most commonly used circuit as far as noise elimination are the filter circuits. They're used to select frequency ranges that you desire out of signals and to eliminate undesired frequency ranges. A high-pass filter is used when you have a lot of DC offset or very low frequency drift. A low-pass filter is used to eliminate the effects of high-frequency noise. And then bandpass filters basically accomplish both in one circuit. The filter order will tell you how steeply the transition occurs from the cutoff frequency from the part of the frequency spectrum that the filter passes to the part that it rejects. And so cutoff is basically defined as where your signal voltage is reduced by a factor of 1 over the square root of 2, or on your frequency plot of input to output to input. So here's an example of a high pass filter. This point right here, notice the filter goes flat, which means as frequency increases, the output of this filter remains flat. Notice at this point it tends to go down. What we're actually plotting here is we're plotting output voltage over input voltage. So we're plotting magnitude of the voltage gain as a function of frequency. So frequency is the horizontal axis, and output over input is the vertical axis. So we can see that at low frequencies on a log scale, our output over input is decreasing. As frequency increases, our output over input becomes constant. So this is a high pass filter because the ratio of output over input is constant, usually 1, for higher frequencies. The low pass filter, notice, is flat at the lower frequencies, and then right at the cutoff frequency, you begin to reduce your output voltage over input voltage ratio. So it's cutting off or eliminating frequencies that are higher than this cutoff shown that looks like a kind of the upper knee of the curve. This 1, 2, and 3 represent what happens as you go up in filter order. So you can see a first order filter does not cut you off as rapidly. A second order filter, the slope is much steeper. A third order filter, it's even steeper. And then finally, the bandpass filter has both a low and a high pass characteristic. So you basically have a range of frequencies that are passed where the output is equal to the input. And then on either side of that, you have a lower cutoff frequency and a higher cutoff frequency. This bandpass filter can also be built as higher order, so you can make these slopes steeper. And that's, in fact, often done. So here are 3 different filter circuits. The low pass filter basically attenuates higher frequencies, and it's shown in figure A. This is the configuration. What we refer to as transfer function as a function of frequency is given by V out over Vn. And so you can see we have this constant RF over Ri that was our original inverting amplifier showing up. And then you've got this term 1 over 1 plus j omega tau. J omega tau is this factor that tells you where your frequency cutoff will occur. And of course you can read directly from here that in this case tau would be 1 over RFCF, these resistance and capacitance in the feedback loop. For the high pass filter, we would have this circuit here. The transfer function is essentially the same. The difference is that our tau is a little bit different, and you can deduce that by factoring out an RF over Ri, and so you have j omega tau in the numerator and 1 plus j omega tau in the denominator. And in this case, you would find that you would get your RICI as the cutoff frequency, this input pair. Then you can combine those to make a bandpass filter. So this is the figure that's shown in your book. I actually advise students that oftentimes it's better to build 2 stages, where you have one stage that takes care of the low pass and another stage that takes care of the high pass. This is just a little easier to troubleshoot, but it would use 2 op amps as compared to 1. Also, if you use 2 op amps in series, so you connect the output of your low pass to the input of your high pass, the advantage there is your transfer functions multiply. So that makes the math sometimes a little easier. So here's an example of frequency characteristics of op amps. So what you want to look at here is here's your sort of your op amp characteristics, and what this figure is trying to illustrate is that you can either get a lot of gain or you can get a lot of bandwidth, but you really can't get both. And so there's this thing called the gain bandwidth product. That's kind of a classic thing in electrical engineering, meaning if you want to amplify a lot, the op amp itself, once you get above a certain frequency, is going to begin to cut off some of your signal output. If you don't want to amplify very much, then you can get much higher frequencies out of your amplifier, but once again, you can't really amplify very much. So that would be sort of the last thing really in op amps that we want to look at in this lecture.